we will do activity 3 right now. Supposed to be in groups, so you guys are in groups, right? I'm not giving you A3 today, so it's okay. But I think you are in a nice group setting. You can discuss with your peers where possible. Teachers will be walking around to help you. So you have about half an hour for these activities. When it's time to review, I will let you know. Okay, so teachers, please go ahead. Thank you. Okay, folks, come. Most of you kind of have some ideas on question 1, right? I mean, I saw most of you somewhere finishing up. So I thought I review first. Would that be okay? I mean that is, I try to make it a bit more time efficient, because if I don't review, right, then everybody will keep talking about question 1. Okay, first question 1A, right, is about the concept of percentage as character. Okay, a relatively simplistic perspective. Okay, y'all need to keep quiet a bit because I don't want to talk too loud. If not, I will lose my voice again. Yeah. Later you can talk. I mean, now let me talk first. Yeah, percentage as character. So we have SP2 versus SP. Okay, so with a greater percentage of S character for SP, that means the lone pair of electrons on the average spend its time closer to the nucleus, more stabilized. Yep, so in that case, I would expect this to be a stronger base. Okay, so this is actually the conjugate base of ethene. Okay, yep, so as simple as that. For part B, identify whether the negative charge can be stabilized. This lone pair will be localized. Okay, so this is known as diisopropylamide. Those of you who did research, this is the famous LDA, lithium diisopropylamide. Okay, it is known as a non-nucleophilic base. This might be a term which you want to learn how to use. Okay, maybe you can say this to impress your H2 teachers. Non-nucleophilic base. So it is a base that is a poor nucleophile. So which means it cannot act as, its ability to act as a nucleophile is not as high as its ability to act as a base because of the steric hindrance imposed by the isopropyl group. Okay, in our case here, the lone pair of electrons can be delocalized into the carbonyl oxygen. Okay, so therefore, my choice will be this. Okay, yeah. Moving on, most people have a misconception that this is a stronger base because it has more electron donating groups. This is actually wrong because it's both of them have one group. Yeah, both of them have one electron donating group because they're all considered one LQ group. Right? There's one center only, right? Yeah. So the main idea is a bit difficult to explain, but it's actually based on solvation. Yeah. Okay, what is the meaning of solvation? Okay, this I think most of you will get it wrong. It's okay, doesn't matter. But I thought we just want to bring this idea to you. Solvation means that this particular conjugate base, right, is more poorly solvated, okay, by its corresponding tertiary butanol, okay, due to the steric hindrance imposed by the tertiary butanol group. Yeah, so because it is less well solvated, that means the lone pair of electron is more available. Then what about methoxide? Or methoxide is a different question because methoxide can form quite extensive ion dipole interaction, or you can say hydrogen bonds with methanol. Methanol is very small, right? So you expect more methanol to surround methoxide as compared to tertiary butanol to surround tertiary butoxide. Yeah, post-solvation is the main reason. It has nothing got to do with more electron donating or less electron donating groups. Okay, then finally, you guys need to draw out your NO2 group. Yeah, because if you don't draw out your NO2 group, you will not be able to check this out. Okay. You'll notice that the lone pairs of electrons over here, right? Okay, we call this the electron source. And this NO2, especially the N-double-O, the electron sink. So when you push electron density, it goes from the source, the sink. But this is not possible for our good friend, the 1,3 position isomer. So therefore, this is a stronger base. Okay. Once your lone pair can delocalize to a greater extent, it will be less available to coordinate back to the H+ or any Lewis acid. Okay, folks, let me know if you have questions. If not, please move on to question 2. Okay, shall we look at question 2 first? Okay, for question 2, there are 2 types of proton. One is here, and one is here. Okay. So we will compare removing either of the proton. Okay, so if we remove HA, this is what we'll get. If we remove HB, this is what we'll get. Then you notice that the middle carbon anion is flanked by 2 electron withdrawing CO, which allows your lone pair to delocalize both ways. It can either delocalize in this direction, okay, or delocalize in another direction. So I can show you how to draw the resonance structures, but you will have to draw them out on your own at home for practice. Okay. Yeah, but for our structures here, you can only draw the lone pair of electrons to delocalize to 1 carbonyl oxygen. So in terms of stabilization, it's less stabilized. Okay. Yeah, so in that case, HA will be more acidic. Yep. Okay. Let me move on to question B. For question B, I think a lot of you think too much because this question is just very simple. Basically, it's just asking you, is the H bonded to O more acidic or the H bonded to N? Purely by looking at electronegative value, O is more electronegative than nitrogen. So therefore, you expect the protonic hydrogen bonded to O to be more easily cleaved because the conjugate base is more stabilized due to the greater electronegativity of oxygen as compared to nitrogen. Okay. Sometimes the reasoning can be quite simple. It need not always be very complicated. Yeah. Okay. There's no resonance to draw. There's nothing to draw. You don't need to draw any resonance here. Structures. Okay. Some of you try to draw the H here, but no need. Because if you try to do that, then you are creating very unstable species. C is the hard one. There are a few protonic hydrogens to look at. Not protonic hydrogen. There are a few H to look at, either HA or HB. The rest no need to look at because you know that their conjugate base will not be stabilized. Okay, so truth to be told, HB is more acidic. Why? Because there's a greater extent of delocalization over 4 atoms rather than just 2 atoms or 3 atoms. Okay, how do we know that? Try to deprotonate and then you can tell. Like this, like this, like this. A greater extent of delocalization. Okay? Is that okay? Okay, I'm sure it will not be 100% okay, but you need to take a bit of time to think through. And my suggestion is to go through some of this on your own at home. Okay. This is the hard one. This is quite hard also. Let me just erase. Okay. You know why this is quite hard? Because if you do pharmaceutical science, right? This kind of structure will come out quite often because you are trying to find structure which can potentially replace carboxylic acid. Why? Why do we want to do that? To make it compatible with our body, sometimes. Sometimes it's not easy. Yeah. So this is an example of a structure that is carboxylic acid-like. How to tell? Of course, you cannot tell now. I have to tell you, that's what then you can tell. This is actually analogous to oxygen. Then this is analogous to OH. Okay, I'm not expecting you all to tell this, and you don't need to tell to do this question, but I just share with you some additional stuff. It's not needed to do this question, okay? Can I stress this? To do this question, you don't need to think whether it is analogous to carboxylic acid or not. It's not important. But I just want to show you this because it's quite interesting. Like, if you do pharmaceutical science, they will usually tell you things like this. Okay, then, but of course, by giving you this clue, you know that this H is more acidic. Okay, then what if I don't give you this clue? Then a bit hard already. Okay. Anyway, let me show you. If I lose, oops, what am I doing? Okay, if I lose that particular hydrogen, then I'm going to get this structure, which allows the negative charge to be delocalized. Can you tell? Can you see? Yeah, so I have to draw out to see. Oh, it's not so straightforward. Okay, I know it's a very steep learning curve. Let's say I don't draw resonance, can. You can use orbital diagram to help you. Like that. Okay, and then okay. Like that. And blah blah. Okay. Yeah, this is a very H2-ish way of doing, but if you can understand this, I think it means you can appreciate some of the concepts. Okay, can I trouble you to do the last bit? Question 2A at least. Sorry, Sorry, there's still question 3. Yeah, I'm so sorry, people. There is still question 3. Okay, so please do question 3 first. If time permits, we'll do at least 2A. Okay, the rest of part B we can't do because we would like to do activity 4. All right, so maybe 5 minutes, maybe. Okay, then I will go through a bit of question 3 and 2A. It's okay to go slow, as in, if you ask me as a teacher, I really don't mind going slow. It's just that time is against us, lah. But it's okay, lah. Anything I don't go through, there's always things to record and then you can go and view, but it's more passive, lah. Oh. Okay, can I address this little thing? Because I thought it's quite interesting question some of you asked. Okay, I don't know whether the other 2 classes, you guys asked the same thing, but I thought I just address this. To once and for all, clear up some misconception. Okay, I mean it's not exactly misconception, but I think it's interesting to ask also, because when I was a student, probably that's something I have in my mind as well. Okay, some student ask me, right? When I lose electron, when I lose the proton here, technically it seems that the negative charge, technically it seems that the delocalization also goes all the way to here. On paper. Okay, but if you read up more, right, this is actually known as cross conjugation, which doesn't give the system much stability. So, okay, why do I say that? Because if you try to draw the resonance structure, right, you see, right? Okay, I delocalize here. I cannot go over to the other side, you know. Do you notice? The only thing I can do is I will break the CO pi bond, and then we'll see what we get. Okay, we're going to get this. Okay, what am I doing here? Because there's an extra. Okay, am I? Wait. Okay, so we're going to get this O minus, right? Now, some of you might be thinking, can what? This lone pair, I can come in, and then something can happen to go to here. Nothing can happen. You cannot push. Because this carbon, right, already has 8 electrons. If I come in, if I simply form this pi bond, right, you have 10 electrons. Something must break. So the only thing that can break is this pi bond. Okay? Then some of you will be thinking, not true. I can do this. You can do this. Can. You have in not this case, other cases. But this is not resonance really. This is called fragmentation. But that's something else. So let's not talk about that, okay? Yeah. So that's why this kind of cross conjugation doesn't lead to stability. Okay, I hope that addressed a little bit. So the best way to check whether is it okay is to see whether you have a continuous overlap like this. In one line, in one line, not crossover. Okay, let's discuss this. Okay, first, proton. Okay, once we have proton, what can we do? We can protonate the carbonyl oxygen. Okay, once we protonated the carbonyl oxygen, the next thing that can happen is I will lose this proton because I need to form a double bond here. So check it out. Okay, so likely that this proton will be lost. So it's like a catalyzed reaction, you know what I mean? Like I take one and then I form the other one, and then I kick out the H+. Do you realize that now I form a double bond? which can technically undergo electrophilic addition from what we learned in H2. Okay, so most of you will do it like that. You do like that. Nothing wrong at this stage, except it's a taboo in chemistry. Because you produce a carbocation directly next to a highly electronegative OH group. Actually, nothing wrong also lah. I mean, most people will simply just lose a H plus. Yeah, and then end of story lah. But usually it will not happen the way you envision. Because where possible, try to have octet configuration in all your atoms where possible. Okay, so normally we want to modify this a little bit. Okay, what we want to do is we want to form the pi bond here to get this, the conjugate acid of a ketone. Then after that, you lose the proton again. Then you get a product. Okay? Can? Am I making sense? Why? Okay, tell me why. What doesn't make sense? Who say no value? Oh, come. Oh. Okay, try again. Oh, thank you. Can Okay, I'm sorry. I don't think we can move on anymore. But what I will do is I will do a video review on part B. Okay, but please go back and work on your part B. It's important for you to feel natural in drawing the curly arrows, to feel at ease. Okay, so go back and do part E. We'll review it. Then we'll release a video for you to look through. Okay, the next thing we're going to do is activity 4. So I'll need the tutors to help me give out activity 4, and at the same time, you guys can take a 5 minutes break. Okay, so that you can rest your mind a little bit. Okay, so we'll begin at about 5:20. Okay, we'll start to give you some ideas. So the things we share here, you can read them up in the. I'm not sure if your batch we share some reading materials for you. There are some free online textbooks, but I think let me check whether it's uploaded for your batch. Okay, but anyway, this is a perspective which you can often look at when you are examining nucleophilic substitution. We are not saying that it's either scenario 1 or scenario 2. We are saying that which one it resembles most. Okay, so I think for scenario 1, we are looking at factors which help us to increase the ground state significantly in terms of energy. So that because the PS is quite close in the energy, yeah. So because of that, the activation barrier via pathway 2 is lower. And then, of course, for scenario 2, which is what you are familiar with, in this case, SN2, where you have a very bulky substrate, it is likely to increase the energy of the transition states very significantly due to the steric repulsion, okay, between the incoming nucleophile and the bulky groups. Okay, so with that, How does that translate into real experimental data? Okay, so we look at real experimental data by looking at table 1. You can look at the relative rates for SN2. So this is methyl bromide. You can see that when we just add and we just replace a methyl group, a H with a methyl group, the rate of the reaction decreases by close to 100 times. Okay, so that tells us something about steric demand when it comes to SN2. And then, of course, we add an extra methyl group, and then it goes to 500. And then, of course, even though this is a primary substrate, but the steric demand imposed by the tertiary butyl group, it'll be good for you to know what this is. Tertiary butyl group. Okay, it's so great that the rate of reaction is a lot slower, but we can take this as a benchmark. And then, of course, for a tertiary butyl bromide, is damn slow, much lesser than 1. Okay, so from this information, you should be sketching scenario 2. Okay, by looking at the fact that the transition state leading to the product, its energy is significantly enhanced. Okay. Some of you might argue, you say that it's not fair because we are looking at quite different things here. Yes, this will change, no doubt. It will not be the same, but it will change marginally. That's what we meant. Okay, then you ask, how do we know? Okay, you know it by, of course, it comes with experience, but largely, when reaction happens between the nucleophile and the substrate center, the shear electronic repulsion or steric hindrance will increase the electronic energy or the energy greatly. Okay, as compared to a substrate alone with substituent, it's not affecting much. Yeah, so we will say for a substrate, whether we are talking about bulky substrate or not so bulky substrates, like tertiary butylamide versus this, we're not going to expect the ground state energy to change appreciably. But when a reaction takes place, that's when this gets shoots significantly. Okay, yeah. So that will be for table 1. And then, of course, for table 2 is the other extreme we are looking at. We're looking at the relative rate of SN1. Okay, using water as a nucleophile. Okay, so in this case, the water is a nucleophile. They did not tell you the solvents in the system, but of course, it's a system where the bromoalkane can dissolve. I mean, if it cannot dissolve, then I think we shouldn't be discussing this. Okay, so likely to be a solvent pair, but that's not important at this stage. Yep, and then we are looking at tertiary butylamide a lot faster than secondary, and then blah blah. So those of you who are familiar with this, you know that we are looking at a carbocation intermediate. Okay, we are looking at carbocation intermediate. Yeah. And then they also ask you to consider the stability of carbocation. And please reference to what you have learned last week on physical organic chem on the Harmon postulate. Okay, it's related. Okay, so if you are looking at energy profile diagram, right? Okay, reaction coordinates. Okay, so let's try to compare. We look at the extreme case, tertiary carbocat. Okay, so for tertiary carbocat, we are probably looking at something like this. Okay, so this is a tertiary C+. Okay. For those of you who can't see, this is a C+. Sorry, it's not written very clearly. Okay, I'll use a contrasting color. Okay, so my carbocation is closer in energy. So this is like a late transition state. Okay, so that means that my transition state has a very strong developing carbocationic character. Yeah, so it resembles energy. So therefore, right, when we are looking at a primary substrate, you can probably envision it to be something like this. Yeah, so if I'm going to draw it, this is a primary TS. I mean, can I put inverted comma? Because the word primary TS is not a correct term to use for tertiary TS. Okay. If I may draw the transition state out, okay, if I may draw it out, then it will probably look like this. Yeah. So versus the primary one. Okay, so we are looking at these two. So therefore, energy profile diagram which goes through a tertiary carbocation will expected to be more stable. Okay. So you can call this a tertiary carbocationic-like transition state. Okay, can? Yeah. Most of you probably wouldn't have reached here. I think we will discuss this later on, okay, via online review, because this needs quite a bit of explanation. Yeah, and we want to go through all the factors which affect substitution. So with that, we will need you all to move on to part B and C. Okay, yeah. Okay. In case you're wondering why are we doing this, in case, okay. So these are the factors that affect the rates of nucleophilic substitution. So what we have talked about earlier on is the effect of the substituent. It's what I call the substrate effect. Okay. Now we are looking at the nature of the nucleophile. This term is invented by chemists, nucleophilicity. Okay, I don't think there's such English word in the dictionary. It's invented by chemists. Yeah. And then later on, we have something called the leaving group. I think in various contexts in H2, your teacher might have told you about leaving group. And then for some reason, they took this out of syllabus, solvent effect, but I will review it online, so it's okay. I also don't know why they took it out of syllabus. So, okay, let me talk about solvent effects. Nucleophilicity. Now, first, okay, we need to establish certain things. These are all measured in protic solvent, capable of forming hydrogen bonds with OH and NH. Okay, first of all, right, let's do a bit of comparison. We will compare between anions in the same group in the periodic table. So in this case, sulfur and oxygen, OH minus versus HS minus. Okay, we'll compare these two. We will also compare between I minus and Cl minus if you wish to. Okay, so you realize that the bigger the anion, the faster the rate. Okay, but however, right, OH minus is a stronger base than HS minus. Okay, so OH minus is a stronger base than HS minus. Okay, so therefore, the relationship between nucleophilicity and basicity is reverse. Okay, so a strong base need not be a good nucleophile. Yeah. Okay, so later on, they will bring out this reason known as polarisability. These are real data. They are not like anyhow make up and then just to feed you and then, yeah. So these are real data. Okay, now, 5. The relative rate between these, some of you might be wondering why we're using these 3, right? Because for all the 3, the negative charge largely resides on the oxygen. There's a reason one. We don't anyhow do things, okay? So let me highlight. So we are looking at OH minus. We are looking at methoxide. Okay, you realize methoxide is a little bit faster than OH minus, maybe about 1.6 times faster. And then we are looking at ethanoids, which is quite slow, but okay. Okay, so what is the relationship between nucleophilicity and basicity? So if you are looking at the same atom, the stronger the base, the better the nucleophile. From here, just from the data alone. How do we know that this is a weaker base? Remember acid-base equilibrium, or organic chem, hopefully. The carboxylate anion, the lone pair electrons can delocalize into the carbonyl oxygen. Okay, these two localize in the O. For methoxide, the negative charge is enhanced by the electron donating methyl group. Okay, so therefore methoxide is a stronger base than OH minus. OH minus, both of them are stronger base than ethanoids. Okay. Okay, so some people call this acetates. Those of you who did research, maybe your professor would have called this acetic acid. Okay, but yeah. Okay, now we are looking at same oxygen, similar species. One is the acid, the other one is the conjugate base. Okay, so from here, obviously, neutral versus charged. If it's charged, it's a stronger nucleophile. Okay, so question 4, 5, and 6, they want you to realize certain things. Like number 1, we are looking at the same group in the periodic table. The bigger the atom, the stronger the nucleophile. If we are looking at the same atom, then the stronger the base, the stronger the nucleophile. If you are looking at the acid, or rather the nucleophile and its corresponding conjugate base, then the one with the negative charge is a stronger nucleophile. Okay, so from here, we want you to tell certain things. So briefly explain whether nucleophilicity is an important factor in determining the rate of substitution in SN1. People, please highlight this. Don't anyhow write exam SN1. It's not important because for SN1, the rate equation involves only the substrates. Yeah, so not important. Okay, Ken. Then I think this is something important. Polarisability. Okay, so can read about it. Yeah. We are trying to debunk a myth. Okay, we're trying to debunk a myth. Actually, historically, right, the topic on halogen derivative has always been taught by telling you that X must be halogen, or at least at the start. Actually, it's not true. So that topic shouldn't be called halogen derivative. There's a legacy issue there. Always start with halogen. Yeah. So the X is what we call a leaving group, because it is a group that departs from the substrate. It may not only be halogen, it can be other things. So, for example, it can be something called tosylates. This structure you might want to know. You might want to know, but you no need to memorize. If you need to do it, we'll give it. This is known as toslate. Very popular structure, often test in exams. Okay, it's a good living group. And then the rest doesn't leave. Okay. Later on, some of you will be doing, or rather, we all will be learning alcohols in H2, right? So normally in alcohols, the OH is not a good living group. Looking at this. Normally, you will convert it into a toslate before you add a nucleophile to replace it. Okay, so this is a very common synthetic rods you will see in research labs in the past. Now they don't do it like that. Yeah, okay, so good to know. I mean, good to know, I don't mean you have to like remember it, but if you happen to come across reading it, yeah, please read. Okay. The change in living group, in this case, for SN2, is likely to, okay, so if I may go back to the first page, my apologies, I need to shift back. Yeah, so it will lower the activation barrier. Okay, so we are likely looking at scenario 2. Okay, Ken? Similar to what we are familiar with earlier on. Okay, I won't go into details of things which we have discussed. So I really urge every one of us or every one of you to go through some of these things which we have gone through with you, and then at the same time maybe go through your lecture notes which we'll give out later. Okay, then finally explain whether the nature of living group is an important factor in determining the rate of substitution is SN1. Yes, definitely, because of the same reason. Okay, the rates of the reaction is captured in the rate determining. I mean, is captured because the substrate is involved in the rate determining step. Okay, solvent effect, I will review it to all of you online. Maybe for now, shall we take a bit of time? Because I think group work helps a lot. Maybe you guys can discuss with your friends. Question 3 on page 2, I think it's an interesting question to do. Okay, can I just review it? Finally, okay. In chemistry, right, we call this kind of group substituent on the benzene, of course. But it's interesting that the substituent has a crucial effect on whether the system undergo a pure SN1, a mixture of SN2, SN1, or more SN2 or more SN1. So in the past, right, people always study what they call substituent effect. So this is known as substituent effect. How the substituent will result in a change in mechanism. And these are the interesting things which we will tend to test you in exams. Give you data and then you can check. Okay, so we look at the benchmark. X equals to H, which means just a common phenol ring. Okay, so you get about 59% of this and 41% of this. You can't really account for this, but except to say that probably I get more SN2 than SN1. Okay, why more SN2 than SN1? Because beta ratio, you can't really tell. Okay, it is a secondary substrate. Carbocation is okay in terms of stability, but not very stable. Okay, but things change when we are looking at OME. And that is why we ask you to try to draw resonance structures in the earlier examples. Because in OME, right, the O methoxy group is able to stabilize the resonance structure, or rather stabilize the carbocation. Okay, so let's say I have a Cl here, like this, right? Technically, I can push out the Cl. Okay, and in the process, results in the formation of this particular carbocation. Okay. Can you see that it is not really a trigonal? I mean, it is not like a carbocation at the plus at the carbon here, but now the whole structure has the octet configuration on every single non-hydrogen. So this is actually preferred. And then this is trigonal planar in geometry. Okay, so trigonal planar. About carbon. So it allows the nucleophile, which is the H2O, right, to approach from the top and bottom plane with near equal probability, which is what you have learned in page 2. So I get 50-50. Okay. Also special because in this case, the carbocation is stabilized. And we have shown exactly why that is the case. Some of you might be very stressed. Wow, I need to straight away see this. No need, no need. You can first draw the carbocation first. If you are not confident, it is perfectly fine to just draw this first. And then after that, show the resonance structure. Okay, no problem at all. You won't be marked down, don't worry. But if you can tell, then easier lah. Oh. Then my NO2 scenario, I think you should be able to tell, because electron withdrawing group, right, prevents the formation of carbocation because withdrawing group destabilize carbocation. Yeah, so in our case here, we get about 50% SN2, 50% SN1. This is the scenario in your in-class exercise 2. Most of you have done it. 50% SN2, 50% SN1. Yeah. Not the same question, but the ratio just nice. Okay. Yeah. That's it for today.